I know actually next to nothing about how data centers function. Maybe I shouldn't say that, but...
This is Seshadri, or Sesh for short. He's a theoretical computer scientist, professor, and by his own admission, no data center expert. Yet his mathematical expertise helped AWS crack the code to $1 billion carbon-cutting data center breakthrough. And it all started with a Slack.
There was sort of a random Slack message saying, is there someone who has expertise in this area of math? And I just casually responded saying, yeah, I know something about that. And he said, okay, maybe we should chat.
The exchange was with Ratul, a fellow professor and Amazon scholar who, like Sesh, lends his expertise to help AWS tackle complex challenges. Sesh's specialty is random graph theory, which is basically the math behind what happens when you build a network by connecting things at random. For Ratul and Giacomo, an AWS applied scientist, Sesh was exactly the expert they needed to help solve a seriously hard networking problem.
We have been working on a new fabric design. When I say fabric, I refer to the data center networks. So how we connect the thousands of routers we have today in data centers.
A network is the backbone of a data center. It determines how every component connects, communicates, and performs, which means implementing a new design is a high-stakes challenge. Traditional data center networks are built like a family tree, with layers of switches and routers directing traffic between servers. It's a reliable design, but a surge in data can sometimes result in a bottleneck. This pushed Giacomo and Ratul to research a different approach.
Basically, the idea is you have thousands of routers in a data centers and you connect them at random.
For over a decade, researchers had argued that by drawing on random graph theory and distributing router connections randomly across a network, you could remove single points of failure and make data transfer more efficient and resilient. The problem was, no one had ever been able to move the idea from theory into mathematical proof or practice. For Matt, AWS's VP of Network Engineering, it was a brilliant but improbable design.
We'd looked at it in the past, but we never thought it would work in production, especially at any sort of scale of production.
Matt was, however, willing to take another look after Giacomo and Ratul presented a promising plan and recruited a math whiz who knew his way around a random graph.
If you picked someone with sort of my training and you just sort of asked them, what is the right way to connect a network? The answer would be, use a random graph. But we never had to think about what are the challenges.
The first challenge, finding the best route without a map. In a data center, routers kind of work like a GPS system. They tell data where to go according to a set of rules or routing protocol. In the existing network, the paths are easy to assign because they're predictable. But in a random graph network, the paths are, random. So finding the best route is much harder.
What we realized is sometimes the shortest path is not the best option.
This realization led to SprayPoint, a proprietary routing protocol.
It's designed to work for random graphs specifically by forwarding data between servers throughout all the possible paths.
The second challenge, controlling the cabling chaos. Modern data centers contain millions of individual fiber optic connections. Building a random graph network manually would require technicians to connect routers to one another at random, creating a mess of crisscrossing cables.
It can be a spaghetti monster, yes.
Keaton is an optical engineer who works out of AWS's Network Product Development Lab. That's where engineers designed a brand new solution to keep the cables under control. Meet the Shuffle Box. It enables randomized fiber optic connections in a controlled, repeatable, and manufacturable way.
It kind of somehow takes that hairball mess and pushes it into this box.
The third challenge, proving it could work with no room for failure.
There's a very big difference when you're operating at AWS scale. There's no opportunity for real experimentation with customer data.
So for 2 years, the team ran endless network simulations. And with Sesh's help, they produced the rigorous mathematical evidence that would give the rest of AWS the confidence needed to test the new network out for real.
It's extremely scary, but it also makes you feel very happy because you managed to, with a great team, to pull this through.
Spoiler alert, the Shufflebox and SprayPoint worked exactly as predicted. For the first time in the industry, a random graph network had been proven to work. And now it's rolling out at the majority of AWS data centers worldwide. It requires significantly fewer networking devices, which means less power consumption and fewer CO2 emissions across the growing number of grids where AWS operates.
What's so different than what we've done before, and it's going to bring significant advantages to our customers in terms of better reliability, better performance, and it allows us to effectively get more network faster for all of the services that demand it.
As for Sesh, he's back in the classroom with more insight into data center functionality and a good story to tell his students.
There are these ideas that may come up, and you might think they won't go anywhere, but once there's some critical mass built, these ideas can help solve really big problems. So yeah, I think it's exciting to see that.